Hello everyone. In this video, we're going to be covering concepts from the course of Chemistry 1411, also known as General Chemistry 1. The topics that we're covering today are going to be quantum numbers, electron configurations, and orbital diagrams. Quantum numbers. Quantum numbers designate specific shells, subshells, orbitals, and spins of electrons. This means they describe completely the characteristics of an electron in an atom. Describe the solutions for the Schrödinger equation, which is the equation used to describe three-dimensional or 3D standing waves and possible energy states for electrons in a given atom. There are going to be four sets of quantum numbers that we're going to talk about. The first is going to be the principal quantum number, and it's going to be designated with a lowercase n. The principal quantum number describes the main energy level, so the energy, or the shell, that an electron occupies. It's going to be a positive integer, so it's going to be a positive number, and normally it will be given, so if you see something like this, so a 2s, don't so much worry about the S right now because we'll cover that later, but the 2 that they give tells you what your principal quantum number is. So if I have a 2s, my n equals 2. If I have a 3s, my n equals 3. So like I said, most of the time it's going to be given, or you can tell how to determine it based off of looking at the periodic table. And we'll be able to go through that more when we hit electron configurations. Energy shells. As the n value increases, so as we go from 1, 2, 3, and so on, the energy shells get farther away from the nucleus. So if I have n equals 2, we're in the second energy shell. So it's kind of depicted in this picture right here. So this black dot right here is the our nucleus, and as we increase in our energy level or energy shell, our n is also going to be increasing. The second quantum number is the angular momentum quantum number, and it's going to be shown by the letter lowercase l. It designates the subshell of our n, so they're all going to kind of relate to each other. So n tells us our shell, and L tells us our subshell, and it's going to tell us the shape of that subshell. So like I said, it indicates the shape of the atomic orbital that an electron occupies. It is equal to the integral values from 0 up to and including n minus 1. So whatever our n is minus 1, it can include everything up to that point. So, like I said, we saw SPD, well, we kind of saw S, but there's also P, D, and F orbitals. And a number value, so whatever our L value is, will correspond with that specific letter. And that specific letter shows us a specific shape. So if my L equals 0, I have an S orbital. If my L equals 1, I have a p orbital. If my L equals 2, a d orbital, and if my L equals 3, it's an f orbital. There's more orbitals past f, however, we're not going to be covering them for this course. So here is kind of how we can sum up everything on a little chart between our principal quantum number and our angular momentum quantum number. So if our n equals 1, then our L is going to equal 0, which corresponds, like I said before, with an S. If our n equals 2, we can have both an S and a p orbital. So this tells us that our p orbitals don't start until we have at least a 2 for our principal quantum number. And you can see that as we get bigger and bigger, we add another subshell. So this tells us how many possible subshells there are. So if our n is 1, we can only have an s orbital. If our n is 2, we can have either s or p, 3 spd, 4 spdf. And like I said, based off of the orbital that we have, it tells us the type of shape that our orbital will be in. So if we have an s orbital, it's going to be a spherical shaped orbital. So it kind of looks like a ball. If we have a p, it kind of looks like a peanut-looking shape. And do keep in mind that the orientation, which we'll talk about later, will change. So it's not always going to be straight up and down. It can be facing towards you. It can be horizontal. So be able to identify these shapes no matter what direction they're facing. Our D kind of looks like, I guess, like a flower, but it's 2 peanuts. It's a double peanut, I guess is what you can call it. And then this is the other shape that you might see when trying to identify it as well. And then your F, I guess, looks more like a flower, so F for flower. But it also kind of looks, if you ever played jacks when you were younger, those little metal things where you bounce the ball and pick them up, it kind of looks like a jack. Our next one is the magnetic quantum number, and it's going to be M sub L. So M with a little L lowered. And it designates the specific atomic orbital within a subshell L. So like I said, they build on to each other. Atomic orbitals within a given subshell differ in orientation in space, but not in energy. So our magnetic quantum number is going to tell us the orientation of our subshell. Within each subshell L value, the ML includes integral values of negative L value to L value. So if my L is 1, my ML is going to be a range. So it's going to be -1 to 0 to 1. So everything from negative L to positive L is included in your ML. The number of ML values indicates the number of orbitals in a subshell. So remember how we said our S is equal to a 0. So if our N is 0 or 1, we have 0 as our L for an S orbital. With 0, our range for ML can only be 0, because you can't say -0 or +0, it's just 0, which means that for an S orbital, we only have 1 orbital. And it'll make a little bit more sense when we see an actual picture of this. So you can kind of see right here. So with our angular quantum number 0, we have the range, like I said, of 0. This tells us that for an S subshell, we only have 1 orbital. For a P subshell, where our L is 1, we have 3, so it goes from -1 to 0 to 1. For D, you can figure out how many orbitals using 2L plus 1. So 2 times 2 gives you 4, plus 1 tells you 5. So you go from -2, -1, 0, 1, 2. Same thing for F. So 2 times 3 gives you 6, plus 1 will give you 7. So you have -3, -2, -1, 0, 1, 2, and 3. So it's that range for your ML. And then finally, our fourth quantum number is going to be the spin quantum number, and it's going to be M sub S. And it denotes the spin of an electron and the orientation of magnetic field produced by this spin. So it's going to tell us if we have a positive spin or a negative spin on our electrons. So we can have 2 values for MS. We can have a positive 1/2, or we can have a negative 1/2. And when we get into our orbital diagrams, it's going to be denoted with either an upwards arrow or a downwards arrow. And each of those arrows will represent electrons. And that's kind of what this is. So as we see this downward arrow right here, that tells us our MS is -1/2, while the upwards arrow tells us that our MS is +1/2. So let's go through an example. We want to know what the quantum numbers are for the following. So we have 2p, 4d, and 5s. So let's go ahead and go to our boogie board so that we can work these out and figure out what and how to actually find our quantum numbers. So our first one, A, is a 2p orbital. And remember how I told you that your n is normally given? Well, it's that number right there. So automatically we know our n is equal to 2. Our L is going to be the letter that they provide for us. Or if they provide us with a number, so if it's not in this format and they provide us with a number, we can use that number to determine our letter. So if our L is equal to 0, it's an S. That's 1, P, 2, D, 3, F. So in this particular case, we have a P. So our L value will be 1. Our ML is going to be that range of our L value. So because we have 1, we have -1, 0, 1. So negative L value all the way to positive L value. And then our MS, because we're not dealing with a specific element, we can say can it be assumed that we have a -1/2 and a +1/2, that you can write both. And that's all we really need to do for this. So let's go to B, and it's going to be a 4D. So our N is given, so we say N equals 4. Our L is a D, so we go here and we say that we have a 2. Our ML is the range, so -2, -1, 0, 1, 2. And our MS, just like we said before, because we're not dealing with a specific element, we do -1/2 and +1/2. Pretty simple, right? So this is very important to remember. This deals with your L values. Let's move that in real quick so you can see what I wrote. There you go. All right, and let's do C. So C, we have a 5F. So our N equals 5. Our L equals, we have an F, so we have a 3. So 3. Our M sub L is -3, -2, -1, 0, 1, 2, 3. So that we have a lot right here. And then I'm going to write the MS right here. So we say -1/2 and +1/2. So for these, that's really all you can do. So you look at what you're given and you use your values to solve. So pretty simple so far. It will get a little bit more complicated once we start dealing with specific elements. But as long as you can understand this general setup, so how to actually determine your quantum numbers like this, you should be okay. All right. So here is a table that kind of tells you how it's going to be set up. And as you notice, it looks like a periodic table. That's because it's going to relate to it. So you'll notice that your helium that is right here, it falls as an S. So we act as if it sits right here by our hydrogen. This entire section right here is our S orbitals, or our S block. This section right here, we consider our P block. This middle section right here, we consider our D block. And this bottom section down here, we consider our F block. And what this tells us is what the maximum orbital is, or the max orbital that we're going to fill for a given element. So let's look at our hydrogen. So our hydrogen would go right here. So you would just look at your periodic table and see how it relates. So it's saying we have a 1s1. So 1s1, let me go to the boogie board. So we're going to cover this a little bit more in depth later, but we've seen this before. We've seen this section. This is the only part that's different. That's going to tell us how many electrons are in our element. So if we have a 1, so our N equals 1 because of this number right here. Our L, because we have an S, it's 0 because we just followed that chart like we did before. Our ML would be 0. And the only thing that changes is our MS. So our MS, because we have 1, so we're going to go over how to draw them later, but when you go to fill in orbitals, you'll draw your up arrow first, and then if you have extra, you'll draw your down arrow. But for this case, we only have 1 electron, so we have an upwards arrow only. So our MS would be positive 1/2. If we had say we were doing a 1s2, so say there was a 2 up here, we would have 2 electrons, so we would draw a down arrow, and so we would have both a positive and a negative 1/2. So hopefully that didn't confuse you too much. So now, like I said, we're going to go more in depth with those configurations, and it's called an electron configuration. The electron configuration of an atom is the shorthand method of writing the location of the electrons in an atom. The level and the sublevel is written followed by a subscript with the number of electrons. So this is what I was talking about earlier. So this is your level or your energy level, which is your N value. Your P tells you your sublevel or your orbital type, so we have a p orbital. And then the number that is superscripted right here is going to be the number of electrons. Before we go on to practicing that, we're going to also talk about orbital diagrams. The orbital diagrams are pictorial descriptions of the electrons in an atom. So it's going to go hand in hand with your electron configurations. It's just the drawing so that you can visually see it. Each electron occupies the lowest energy orbital. So you're going to go from the lowest all the way to the highest until you have to stop for a given element. The Pauli exclusion principle says that only 2 electrons can fit into a single orbital. Still, all the up arrows then go back and fill the down arrows. So let me explain what this means. So we said that a p orbital could hold 3 suborbitals. So this, let's say, is a 2p orbital. What it's saying is that we can only have 2 electrons per suborbital. So it means we can have 1 electron here, 2, because we have to fill all of our up arrows first, and then we can start to fill our down arrows. Per line, or you can see it sometimes as a box, as a circle, you can only have 2 arrows per line, box or circle. And those 2 arrows are going to represent electrons. So this is what they're going to look like. So if I have an s orbital, I have 1 line. I do lines, but like I said, you can do boxes, you can do circles, whatever you want as your orbitals, you can draw. But I do lines just to make it simple. So remember, your S starts at 1, and so I have for an S orbital, I have 1 orbital. For P, I have 3 orbitals, because remember, S is only a 0. P is -1, 0, 1. D is -2, -1, 0, 1, 2. And for F, we have -3, -2, -1, 0, 1, 2, 3, which is why we have 7 orbitals. And in each of these orbitals, we can fit 2 electrons. So if I have an S orbital, I can have a maximum of 2 electrons. If I have a P, I can have 2, 4, 6. I can have a max of 6 electrons. And you're going to follow this trend. So D, we have 5 orbitals, 2 in each, so we can have a max of 10 electrons in a D orbital. And then for F, we have 7, so 7 times 2, we can have 14 electrons. So here is a visual representation of a correct and an incorrect way to draw an orbital diagram. So in this instance, they're doing boxes. So a 1s has 1 orbital. We can fit 2 electrons in. 2s, it's still an s orbital, so it has 1 box. Fit 2 electrons in. P orbital, we have 3. But remember, you have to fill your up arrows first. So you do 1, 2, and if that's all the electrons you had, then you stop. This one is incorrect because they did an up and a down arrow before filling in all of those upward arrows. So that is why our second example right here is incorrect. So example, write the electron configuration for the following orbital diagrams. So we have 3 different orbital diagrams. So let's do A first. So for A, we have a 1s orbital with 2 electrons in there. Then we hit the 2s, which has 1. And they showed a 2p, but there's nothing in there, so we don't have to draw it. If there's nothing in it, it means it's not being used. So this is the orbital diagram we have. So this line right here represents my orbital. These arrows represent my electrons. So the electron configuration is that written out version. So we have a 1s, so we write 1s, and then the superscript is going to be how many electrons. So we have 1 electron, 2 electrons. So we have a 1s2. We then move on to our next orbital. So we have a 2s, so we say 2s. We only have 1, so we say 2s1. And that's all we have to do. So you just write out what you see. So for the second, we have a 1s orbital with 2 electrons, and we have a 2s orbital with 2 electrons. So our p orbital, nothing in there, so we don't worry about it. So this is what our orbital diagram looks like. So we say 1s, we have 2 in there, so we say 2. We have a 2s, so we say 2s. We have 2 electrons in it, so we put 2. And that's the end of our orbital diagram, so that's the end of our electron configuration. So we have a 1s2, 2s2 as our configuration. And then now C, we have a 1s orbital, a 2s orbital, and we have an electron in that 2p orbital. So we have 2 electrons in our first, 2 in our second, and 1 in our p orbital. So this is what it looks like. So we hit 1s, we have 2 in there, 2s with 2 in there, and 2p with 1 in there. So that's all we have to do. It's pretty simple when one is given to you and you have to determine the other. So now we're going to do the exact opposite. We're going to go from our electron configuration and have to draw out our orbital diagrams. So for part A, we have a 1s2, a 2s2, and a 2p2. So let's go to our boogie board and start to draw this out. So we have an S, which means we only have one orbital. So we draw 1. You write out what orbital it is. So 1s, there's 2, so you do 1, 2. We move to our 2s. An S has one orbital, so you say 2s has 2, so you do 1, 2. And then we hit our 2p. P jumps up to 3. So as you move up in orbital, so an S, then P, then D, then S, S has 1, you add 2 on, and you get P, which 2 plus 1 gives you 3. So P orbital will have 3 electrons. If I moved up to D, you add 2 more, so a D has 5 electrons, or 5 orbitals, sorry. So in this one, we have 2. So we're going to go 1, 2, and that's all we have to do, because we filled everything in. So let's go to B. So for part B, it's 1s2, 2s2, and 2p3. So it's pretty similar to our last one. So we write out the orbital, 1s, there's 2 electrons, 1, 2. We have a 2s with 2 electrons, so 1, 2. And we have a 2p, so p is 3, so 2p, and we have 3 electrons, so 1, 2, 3, and we're done. And then part C. So C is 1s2, 2s2, 2p4. So we say 1s with 1, 2, 2s with 1, 2, and then 2p, so my 2p with 4. So we say 1, 2, 3, 4. So after I fill up all of my up arrows, I go back and do my down arrows. So just so people aren't confused, remember you have to fill one orbital at a time. So even though you can't write them out and then just do all up arrows for everything. You have to fill one orbital at a time. So you'll do the up arrow, then down arrow for S, then your other S orbital, and then your P orbital. All right, so writing electron configurations and orbital diagrams for specific elements. So you'll notice that you always saw the 1s, then the 2s, then the 2p on our last example. The reason why we see this is because you have to read it kind of like a book. So you're going to start from the top, reading from left to right. So you're going to hit your 1s orbitals first, and then you come back and you hit your 2, and you go across to hit your 2p. Then you start back over and you hit your 3s, then your 3p. So this tells you the order that you're going to be writing your configuration. And then you hit 4s, 3d, 4p. So remember, your s's will start at 1, your p's will start at 2, your d's will start at 3, and your f's will start at 4. Your this number that is right here is going to tell you what your N number is. So if I say I give you this one right here, your N number is 4. And then you can find your L, ML, and MS from the other information. The letter that is right here tells you the type of orbital it is. And then these numbers right here, those superscripted, are going to tell you how many electrons are in that orbital, or that's the maximum amount. So if I say the element that is located right here, This is going to be the maximum amount that you can have for that specific element. So whenever you go to write it out, so where was it? Let's say this one right here. So we stop at a 3p1, but we have to hit everything that comes before it. So you're going to go through your 1s, then your 2s, through your 2p, through your 3s, and then finally you stop right here. So you hit all the way to a 3p with 1 electron. And we'll be able to see how this actually works as we get through some practice questions. So it says, write the electron configuration and the orbital diagram for these specific elements. So we have F, we have K, and we have V. So let me exit this real quick and open a periodic table. So ptable.com. So our first one is F. So remember, your S's are over here. So you go through a 1s orbital. So I'm going to write it now, but you'll see it whenever I move over. So we go through a 1s orbital with 2 electrons in each. You then come back and you hit through the 2s orbital. And you go through both. So you hit through 2 electrons. And then you hit your 2p. So this is where your p block starts. So you hit 2p and you count to F. So 1, 2, 3, 4, 5. F is the 5th element in there, so you only have 5 electrons in your p orbital. So this is kind of what it looks like. So we said we went through the 1s, we went through 2 elements, we went through the 2s, we went through 2, and then we hit the 2p, and we got to the 5th element. So as you move through each element, you're going to hit an extra electron. So this is the electron configuration. Now we have to draw the orbital diagram. So your S's is a 1 line. You say 1s, we have 2. So 1, 2, 2s. We have 2 electrons, so 1, 2, and then we hit 2p with 5, so 1, 2, 3, 4, 5. And there's actually a trick to ensure that you have the correct configuration. You can count the electrons. So you have 5 electrons plus 2, that gives you 7, plus 2, that gives you 9. So if you go back to your periodic table, you see that number right there, right at that top. So let me see if I can go around. Nope, it doesn't want to work with me. So the top number on that fluorine is a 9. That tells you that your protons are 9, and your protons and electrons will be equal to each other. So you have a 9 there. That means you hit the correct number of electrons in your configuration. So you're good. Our next one is K, so potassium. So this one is going to be a lot longer because you have to go through a lot more orbitals. So we hit through our 1s and we hit through both of them. So we have a 1s2. We come back to the beginning, we go through the 2s. So we hit through 2 of them, so 2s2. We hit the p orbital, so that's a 2p. And we hit through all of them, which is 6. We then come back to the beginning and we hit through our 3s. So we hit 3s and we hit through both, so we say 2. We hit our 3p, so we say 3p, and we hit through all 6 of them. And then we come back down here and we hit our potassium. So that's a 4s, and it's the first electron in it, so we say 4s1. So this is what the configuration looks like. So we had to hit through all of these just to get to right here. So now we can draw it. So we say 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s, 2, 3p, 6, and then 4s, 1. So that would be the electron configuration and the orbital diagram for potassium. Now one more. We have V. So got even longer, and now we're hitting a d orbital. So we have to go read from top to bottom, left to right. So we hit our S. So we say 1s, 2. We then go through our 2s. So 2s, 2, because we went through both of them. We hit our 2p. We go all the way through, so 2p, 6. Go back and we hit our 3s. We go through both, so we hit 3s2. We go through all of 3p, so 3p6. Go down to our 4s. We go through both, and then finally we hit our 3d. D has 1, 2, 3, because we're looking for this one, so we have a 3d3. So let's go to our boogie board so we can see how to write it. So here is our electron configuration for V. Now we have to draw it out. So we have a 1s with 2. We have a 2s with 2. We have a 2p with 6. We have a 3s with 2, 3p, 4s with 2, and then it'll be a little cramped up right here, but remember a D has 5. So we have 5 lines right here. This one's kind of short, but this is our 3D orbital, and we say 1, 2, 3. And then that would be our electron configuration for V. And just as a reminder, we covered it before, but remember, you can go to orbitals and it shows you where the blocks are. So the pink are my S block, the yellow is my P block, the green is my D block, and that little purplish blue color is my F block. And if you look, so let's say we go to our V, it's kind of small, but right up here, you can see the configuration. So we said we hit through 1s and there was 2. We hit through our 2s, then our 2p, our 3s, our 3p, our 4s, and then we hit our 3d with 3 electrons in it. So it just kind of verifies and it tells you your electron configuration right up here. It's a good tool to help you study, but don't overuse it because you do need to know how to do it on your own for an exam. All right, so we'll go back and talk about the D block rule. The D block of a periodic table has a rule that makes it different from the other in regards to the 4th and the 9th element in its period. So let me escape real quick and show you what I mean. So we go to 1, 2, 3, 4, so it's referring to these elements right here, and then to these right here, so the ones that are almost halfway and almost completely full. The D block prefers to be either halfway, so all the way to that 5th, or completely filled all the way to the 10. If the 4th or the 9th element, it's going to pull from that previous S orbital. So remember how we hit, let me go ahead and show you real quick, how we have to hit this S orbital right here before we can get into the D block. So there's 2 electrons right here before we hit it. It's going to pull one of the electrons from our s orbital and put it into our d orbital for it to be able to get either halfway or completely filled. And hopefully it'll make a little bit more sense when we look at this picture. So chromium, which is going to be the fourth element in that D block, you would assume it would be a 4s2 3d 4, but that's not what it wants to be. It wants to be a 4d5, or sorry, a 3d5. So this is that s orbital I was telling you that comes right before it pulled one of the electrons from right here, and it put it in this spot right here. So it has at least one electron in each of its suborbitals. And then same thing for copper. Copper is the 9th element in that D block. So it's going to pull one of the electrons from the s orbital, and it's going to put it right here in that d orbital. That way it can be completely filled. And you would just have to write your electron configuration to match what you did. So you wouldn't have a 4s2, you would have a 4s1 3d10. So we're going to practice this. It says write the electron configuration and the orbital diagram for the following. So we have MO and we have AG. So let's exit and go to our periodic table. So MO is the 4th element in our D block. So the first thing we need to do is we can choose whether or not we want to draw it first or if we want to write out the configuration. So I'm going to draw it and show you how it's going to move. So we know we hit through our 1s orbital right here. So we say 1s with 2 electrons in it. We then go to our 2s with 2 electrons in it. We hit our 2p with 6 electrons in it. We then hit our 3s with 2 electrons in it. We hit our 3p with 6 electrons in it. We hit our 4s right here with 2 electrons, our 3d with, this is going to have 10 electrons in it. We hit our 4p with 6 electrons in it. And this is where it's going to get different. So we have our 5s, but remember this MO is going to pull one of the electrons, so it's only going to have 1 electron in it. And then we hit our 4D, and in place of it having 1, 2, 3, 4, because it pulled that electron, it's going to hit 5. So it's going to look as if it's right here, but it really only has enough electrons to be MO. So it's going to have 1 electron in each of its orbitals. So this is kind of what it looks like. So it pulled that electron that would have been right here as a down arrow, and it put it right here. So this is what the orbital diagram looks like. So when we draw it, or when we write out the configuration, we say 1s2, because we have 2 electrons, 2s2, 2p6, 3s2, 3p6, 4s2, I'm going to finish writing it right down here, 3d10, because there's 10 arrows in it, 4p6, 5s1, 5s1, and then 4d5. So this is what the D rule is. So it will pull from the s orbital that comes before that d, and it will place that electron in the last orbital in that d orbital. So it can either be halfway or completely full, but it only pertains to the fourth or the ninth element. So we dealt with a fourth element, so now we're going to deal with a ninth element, Ag. We're right here. So I'm going to erase everything that was there before. So we're just dealing with Ag, which is silver. So we have a 1s2. Nothing else there, so we go down to 2s2. We hit 2p6, because we go through all of these right here. Go back here and we hit 3s2, 3p6, 4s2, 3d10, and then we hit our 4p, so 4p6, and then we come back, we hit our 5s, but remember, this is the one right before, this is the s orbital before we hit our d orbital that contains our element. So it's not going to be a 5s2, it's going to be a 5s1. And then we hit our 4d, and because it's right here and it pulled that electron, it's going to be a 4d10. So this is the electron configuration for it, and now we just need to draw it. So we have a 1s2, so s, 1s, and we have 2 electrons, a 2s2, 2p6, 2, 3, 4, 5, 6. We then hit 3s2, 1, 2, 3p6, 1, 2, 3, 4, 5, 6, 4s2, 1, 2, 3d10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4p6, so 4p, 1, 2, 3, 4, 5, 6. We hit our 5s1, so we say 5s with 1 electron, and then 4d10, so 4d. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this would be our orbital diagram for silver. So let's go back to our PowerPoint and talk about probably the best thing that has happened, the condensed electron configuration. So it makes your life so much easier doing a condensed version. So it's the easier and faster way of writing an electron configuration. The first step is to find the element you want to write the configuration for. So whatever it is it's telling you, so whether it be silver, whether it be oxygen, whatever it is, you just look at it on a periodic table. In a bracket, you're going to write the noble gas, so the thing that was in that 8A column or 8A group, and write that inside the bracket. And then finally, everything that happens after that noble gas, until you hit that element that you're looking for, you're going to finish writing the configuration for it. And it'll make a little bit more sense when you look at this picture. So for this example, we're trying to write the condensed configuration for zinc, so Zn right here. So step 1 was to find our element. Our element is right there. Oops. Our element is right here. Step 2 was to find the noble gas that comes before. So you go up to the previous row and you go all the way down. So AR is our noble gas that comes before it. So we put it in a bracket just like you see right here. And then you have to write everything that comes after that. So after you hit the AR, you come back down and you hit that 4s orbital. So you hit 4s2, so you write it right here. And then you go all the way to your 3D, so you have 3D10 to get to zinc. So this is the condensed version of the configuration for zinc. So let's do a couple of our own. So we have, for part A, we have K, part B, we have O, and part C, we have Cl. So let's exit and go to our periodic table. So our first one is K. So we located our potassium element on the periodic table. We then have to pick the noble gas that comes before. So you go up to the previous row all the way down. So AR is our noble gas that comes before. So we're going to put a bracket and put AR right there. We then have to write everything that comes after it. So AR, we go back down to our previous row and we automatically hit our element. So that is a 4s1 because it's the first element, so it has one electron and we're in our 4s orbital. So AR 4s1 is the electron configuration or the condensed configuration for K. Now let's do oxygen. So we have oxygen. Let me go back here. There we go. So the noble gas that comes before is going to be helium. So in a bracket, we're going to say bracket HE, and that's our step 1 or step 2. So after that, we write everything else that comes after it to be able to get to oxygen. So we hit the 2s2. So we say 2s2, and we go to our 2p. So 2p, and we hit 1, 2, 3, 4. So we have a 2p4. So He 2s2 2p4 is the condensed configuration for oxygen. Now we have one more. So we have chlorine. So chlorine, the noble gas that comes before is neon. So in a bracket, we put Ne, and then we have to write everything that comes after it. So we go down from there and we hit our 3s. So we have a 3s2, and then go and you hit your 3p. So 3p, 1, 2, 3, 4, 5. So we have a 3p5. So our noble gas that comes before, and then everything that comes after to where we can hit our element. So this is the condensed configuration for chlorine. Let's go ahead and bring our PowerPoint back up. And that wraps up everything that we have today. So let's do a brief overview of everything that we covered. The first thing is quantum numbers. We covered principal quantum number, which is N, and it's going to tell us the size of our orbital. So the energy or the size of our orbital. The next is the angular quantum number, which is our L, and it's going to tell us the shape of the orbital. So if it's an S, it's a sphere, P, it's a peanut, D, it's a double peanut, and then F is a flower or a jack. And then magnetic quantum number, which is ML, is going to tell us the orientation of the orbital. So whether it's up and down, side to side, pointing straight at you, it's going to tell you the orientation that it's going to be at. And then finally, we have magnetic spin quantum number, which is going to be MS, and that's going to tell us whether our electrons are spinning in a positive direction or a negative direction. We then hit electron configurations, where we covered full configurations and condensed configurations. And then we also covered the D block rule. So remember that applies to your 4th element and your 9th element on that D block. And you're going to pull an electron from your previous S orbital and put it into the D orbital so it can either have a half configuration or a full configuration for that D block. And then finally we covered orbital diagrams, which is pretty much goes hand in hand with your electron configuration. You're just drawing out what you already wrote. So remember that if you have an S orbital, it's going to be 1 line, box, or circle. P will be 3, D will be 5, and F will be 7. And to figure out how the maximum amount of electrons that can fit in it, you simply take how many orbitals there are, multiply it by 2, and that's how many can fit in that one orbital. All right, well, that's all I have for today. Thank you, and I hope this video is helpful.